Okay, so we have seen the various symmetry elements and symmetry operations. We have seen that there is a symmetry element for a plane, okay, and the operation was reflection, and we used sigma to denote this. Then there was a point, and the operation was inversion, and we used I. And then we talked about an axis. So we had two things. We had one was proper rotation. This will be denoted by Cn, and the other thing is an improper rotation, Sn. Okay, so we had already discussed sigma and I. Now I'll briefly give you examples of proper axis and proper rotations, and then we'll go to improper axis and improper rotations. Okay, so suppose I have a planar molecule of the type A, B, B, B. Okay, A, B, Q. Now it's clear that if I take a line perpendicular to this, okay, that acts as an axis of rotation of that acts as a axis for proper rotations, in the sense if I rotate by 120 degrees, okay, then I'll get an equivalent configuration. Okay, so if I call this 1, 2, 3, okay, then you rotate by 120 degrees, you get something that looks like and this becomes 1, 2, 3. This is an equivalent configuration. Okay, equivalent configuration. Hence we say that this is a symmetry operation. Okay, this symmetry operation is denoted by C3, okay, where 3 stands for 360 by 3 equal to 120 degree rotation. Okay, so this is a general symbol that is used to denote proper axis. Okay, so now if you have an axis, if you have a C3, if C3 is a symmetry operation, clearly C3 times C3, okay, this is equal to C3 square, is also a symmetry operation. Also a symmetry operation, and C3 times C3 times C3 equal to identity. Okay, so C3 or C3 cube equal to identity. In fact, in general Cn raised to n equal to identity. So this C3 axis is perpendicular to the plane of the board. Okay, so this is the C3 axis. Now other axis in this molecule, are there other axes of rotation? Now you can see that if I take an axis this way, okay, and I do a rotation about this, okay, so this is a C2 axis. Okay, so if I rotate by 180 degrees, then this 1 and 2 just get flipped. Okay, so each of these is a C2 axis. So it has 3 C2 axes. This is perpendicular to C3 axis. Okay, so there are 3 C2 axes, 1, 2, 3. Okay, and they are perpendicular to this C3 axis. Now we notice that we had a C3 and we generated 3 C2 axes. Okay, so is there something because we had a C3 axis, we generated 3 C2 axis. Now suppose you had a C4 axis, suppose you had a molecule that had a C4 axis. Okay, so suppose you had AB4. Okay, so this is a molecule with a C4 axis, So the axis perpendicular to A is a C4 axis. Now again each of these is a C2 axis. this is also a C2 axis. Okay. Similarly, you can have other C2 axis like this and another C2 axis like this. Okay. So, the point is somehow in this case the fact that we had 3 C2 axis that allow the fact that we had a C3 axis allowed us to generate 3 C2 axis. Okay. And in this case the fact that we had a C4 allowed us to generate 4 C2 axis. Okay. We can say this in general. In fact, if you had an odd number, then we could have generated 5 equivalent C5 axis, 5 equivalent C2 axis. If we had a C5 axis, we would have generated 5 C5 axis. So, say 5 C2 axis. So, for example, if you had A, B, 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 if you had something like this, and this was a so if this was a C5 axis, then you would have had one. You would have had two. I should show this slightly differently. So the C5, then this will be like so 5 C2 axis. So C5 implies 5 C2 axis. So, in general, if you had a C3 axis and you had one perpendicular C2 axis, then you would have 2 more C2 axis. Okay, so this is the general thing. So, if you had a C5 and you have one perpendicular C2 axis, then you would also have 4 others. If you had a C3 and you had one perpendicular C2 axis, you would have 2 other C2 axis. Similarly, if you have a C4 and one perpendicular C2 axis, you will have 4 others perpendicular C2 axis. Okay, so this is a general rule that is to be followed whenever you are identifying the various symmetry elements. Okay, there is one more point about this C3 axis, which I will again illustrate using this molecule. That is the following. So it is the following. So what we have seen is that one C3 and one perpendicular C2 implies 2 more perpendicular C2. Okay, so one C3 axis and one perpendicular C2 axis implies 2 more perpendicular C2 axis. Okay, similarly, one C3 and one sigma V containing C3 implies 2 more sigma V containing C3. In the sense, what would be a so C3 is perpendicular to the plane of the board. Okay, so this is a sigma V that contains C3. This is a sigma V because if you reflect about this, then this B gets moved to this B. So if you have one sigma V, okay, and you have the C3, then you can generate another sigma V and a third sigma V. Okay, so you'll never have a molecule with just one C3 and just one and only one sigma V containing that C3. Okay, you'll always have 3 sigma V's containing that C3, just as you would never have a molecule having just one C3 and having one C3 and just one C2V perpendicular to the C3. Okay, so these are rules of thumb that you keep in. Okay, so that when you are counting when you are listing all the symmetry elements of a molecule, you don't miss any of the symmetry elements. Okay, so let us take the example of CH2Cl2. Okay, and let's try to see how many proper rotations it has. So CH2Cl2, I'll just again we'll use our representation in terms of the cube. So, the carbon atom is at the center and you have 2 H and 2 Cls. So, I will call this Cl and these 2 are H, and the carbon atom is at the center. Okay. So, we call these Cl, Cl, H, H. Okay. Now, does this have any proper axis of rotation? Okay. Now, in order to answer that, it helps to, I mean, this cube is actually a very good picture of a very good way to see it, because you can immediately see that an axis that goes this way, that passes through the center of the cube and then comes out from the other side. So, this axis, let's show it more accurately. So, it comes right through this way, goes through the center of the cube and then comes out from the other side. Okay. So, this axis is a C2 axis. C2 axis, because you rotate by 180 degrees, then the carbon is on this axis. These two are at opposite ends. So, this chlorine will come here and this chlorine will come here. Similarly, this hydrogen will come here and this hydrogen will go there. So, overall this is a C2 axis. Okay. Now, are there any other C2 axis in this molecule? Okay. Now, you would think if you try this, then when you do a 180 degree rotation, this chlorine will get swapped with hydrogen. So, you do not get any equivalent configuration. Okay. So, this is a symmetry operation. Whereas this C2 is not a symmetry, And in fact, it turns out that this molecule has only one C2 axis. Okay. So, one C2 axis, one axis for rotation by C2. Now, you go back to thinking what should be the property of a molecule that has a rotation axis. Okay. Now, if you look at this has one odd atom, okay, one carbon, okay, but that is at the center. Okay. So, whatever axis you have will pass through that. Then it has 2 chlorines and 2 hydrogens. Okay. Now, if you have an axis passing through none of these are collinear. So, if you have an axis passing through the hydrogen and the carbon, then about that axis there would be one odd hydrogen atom. So, that cannot be an axis of rotation. Similarly, if you had an axis passing through the chlorine and a carbon atom, about that axis there would be one odd chlorine atom. So, it cannot be a symmetry element. So, the only symmetry element that is possible is that bisects both the hydrogens, both the hydrogen the segment joining the 2 hydrogens and the segment joining the two chlorines, and passes through the carbon atom. Okay. So, that is the only one that can be a axis of rotation. Okay. So, in this way you can sort of justify what the axis of rotation should be. Okay. And just for completeness, I will show the methane molecule. So, what are the various rotations? So, what are the rotations of this molecule? Okay. So, okay, you have a carbon at the center and you have 4 hydrogens. Carbon at the center. Okay. So, what are the 4 rotations what are the various rotations that are possible? Now, just as in the case of CH2 Cl2, we had an axis that went this way. Okay. So, we said that this was a C2. Now, this axis, since all are hydrogens, so this will also be a C2 axis, and similarly the perpendicular direction, this going into the board and coming out from the other side, that will also be a C2 axis. Okay, so we have 3 C2 axes. Okay, are there any other rotations? Okay, so are there any other rotations? And the answer is that yes, you have more. Suppose I take an axis passing through a hydrogen and one of the carbons. A carbon and one of the hydrogens. So passing through the carbon and one of the hydrogens. So for example, you take this axis. Now about this axis, there are 3 hydrogens, okay, located symmetrically about this. Okay, so this is a C3 axis. So if you look at the 3 hydrogens, you do a 120-degree rotation. This hydrogen will come here, this hydrogen will go here, and this hydrogen will go here. Okay, so the 3 hydrogens will get twirled, will get swapped in that way. Similarly, you can have C3 axis passing through a carbon and any of the hydrogen atoms. So you have 4 C3 axis passing through C and one of the H atoms. Okay. So you say that methane has 3 C2 axis and 4 C3 axis. Okay. So in this way, for any given molecule, you should be able to identify which are the reflection elements, which are the inversion, whether it has an inversion or not, and if it has, you should be able to identify it, and then which are the various proper rotations that are there, if there are any. Okay. Now obviously, suppose I take a molecule like C, H, Cl, Br, I. So if I take a molecule like this, then it has no rotations. Okay, so it has no rotations. Okay, and of course it has no reflections, and it has no it doesn't have a point of inversion. So no reflections, no point of inversion, or rather, okay, so no point of inversion. Okay, and we'll show soon that it doesn't have any improper rotation also. So we'll show that in a few minutes, that it doesn't have any improper rotation also. Okay, so the last thing we'll talk about is improper rotations, and we'll again do that through illustrative examples. So what is an improper rotation? An improper rotation, it is denoted by Sn. So this is equivalent to Cn followed by reflection in a perpendicular plane. Okay, so you do a Cn operation and then you reflect in a plane perpendicular to Cn. Okay, now let's go back to our favorite example, the AB3 molecule. Okay, this is a planar AB3 molecule, and you can see that this C3 axis. So you have a C3, okay, and you also have, and this plane, the plane containing AB is also a, since it's a planar molecule, it's also an operation of symmetry. So C3 times sigma H equal to S3. Okay, in this case, both C3 and sigma H are symmetry operations. So C3 sigma h is also a symmetry operation. Okay. So, this is a very trivial case in which you have an S3 where you have both a C3 and a sigma. Okay, but then we'll come to cases where you don't have C3 and sigma and still you have S3. But before that, a question that you might think of is Cn sigma in a perpendicular. I'll just draw it as perpendicular. Is it equivalent to sigma perpendicular Cn? So, is this the same? Okay. So, in other words, do the operations Cn and sigma in a plane perpendicular to Cn, do they commute? And the answer is yes. So, rotations and reflections in perpendicular commute. Okay. So, whenever you have a rotation and a reflection in a perpendicular plane, the order does not matter. So, whether you do the rotation first and then the reflection later, or you do it the other way, you get the same result, and this is fairly easy to show. Okay. So now the next thing is, can you find a molecule that has that does not have a C3 axis, it does not have a sigma h, but it has a S axis. Now, to do this, we will look at an example and then it will become clear. Okay, so we will look at staggered and eclipsed conformations of ethane. So, let us look at ethane. Okay, so on this side I will show staggered, and on this side I will put eclipsed conformation. Okay, so in the staggered conformation of ethane, it looks something like this. So you have a carbon here, another carbon, and then you have hydrogens, and on this side you have them staggered. So if these three form a triangle this way, then you can show them in the following way. Okay, so they will go this way. Okay, so in other words, see if there is a colored chalk. Okay, so in other words, I can show this in this way. I can show this as and this one I can show as. So, this is the staggered conformation. The eclipse conformation, okay, and this passes through this. Okay. The eclipse conformation, on the other hand, will have both of them pointing the same way. So, both of them pointing the same way. Okay. So this is a way to visualize the staggered and eclipse conformations. Now notice, in the case of the eclipse conformation, this axis is a C3 axis. Okay. So, if you rotate by 120 degrees, this H will come here, this H will go here, this H will come here, this H and these three H's will also rotate. So, you get it's a C3 axis. Okay. And also this is a sigma. Okay. So, this is a sigma and this is a C3. Okay. So, therefore, this is an H3. So implies you have S3 axis. Okay. So, in the case of eclipse, you have the S3 axis. Now, in this case, if you rotate by 120 degrees, okay. Yeah. So, this is a C3, okay, but this is not a sigma h. This is not a sigma h, okay, because if you reflect it, then this triangle will be in this direction, and this will be in the opposite direction. So, okay, so no sigma. Okay, so this does not have sigma. Okay, so in other words, this is not a plane of symmetry. However, okay, so it has a C3, it has no sigma. However, if you can do one thing, you can rotate this by 60 degrees. Okay, so if you rotate by 60 degrees, okay, then what you will get is so let us do rotation by 60 degrees. So, rotation by 60 degrees, okay, that will give you. So in that case, this h will come here, this h will go here, this h will go here. So, you will get something that looks like h on top, and then you have your two C's, okay, and then you have the bottom two. What will happen is this h will come here, this h will go there. So, you will get something like h. Okay. So, essentially it is as though this came down and this went up, right. So, this inverted triangle is up and this triangle is down. Okay. And so, now if you do a reflection, if you follow R60 by sigma, you get back the original conformation. You get back the original configuration. So, or you get back an equivalent configuration. So, it has S6. It has an axis S6 axis. So, this is S6. It is a C3 axis, but it is also an S6 axis. And notice no C6. It is not a C6 axis, and there is no sigma. So, there is no C6 or sigma, but it has an S6 axis. Okay, so the staggered ethane is a good example of a molecule that has an S6 axis, even though it does not have a C6 axis or a sigma axis or a sigma plane. Okay. Similarly, we will look at another example soon. So, suppose you take CH4. Okay, so it has we said that it has 3 C2 and 4 C3 axis. Okay, now each of these C2 is an S4 axis. Okay. So again you can see that quite easily. So, if I draw a tetrahedron, so you have these 4 hydrogens, okay, and you have the carbon in the center. Now we said that this is a C2 axis. Okay, so this is a C2 axis. So, if you do a 180 degree rotation, these two get switched and these two get switched. Okay. Now, if you do a 90 degree rotation, if you do a C4, okay, then what you will get is so what you will get is the following. This hydrogen, if you do a 90 degree rotation, this hydrogen will come here, this hydrogen will come here. So, you will get something that looks like this. Similarly, this hydrogen will go here, this hydrogen will come here. Okay. So, we just did a 90 degree rotation about this axis. Now, if you do a sigma, if you reflect about this perpendicular plane, okay, then what will happen? This hydrogen will come here, okay, this hydrogen will come here. Okay, so, what you will get is this hydrogen. So, I will do one thing, I will just call it 1, 2, 3, 4. So, when you do the 90 degree rotation, then this becomes 4, 3, 1, 2. Okay. Now, if you do a sigma, then 2 comes here, 1 comes here, okay. Similarly, 3 will get reflected down here. So, 3 will end up here and 4 will get reflected down here, 4. Okay. So, that is what you have 1, 2, 3, 4, and you can see that this is completely equivalent to this. Okay. So, 1, 2, 3, 4. So, it is as though 1 went here, 2 went here, but the locations are the same. So, this is equivalent. Okay. So, S4 axis, but no C4 or sigma, no C4 and no sigma. Okay. So, so this is another example, another non-trivial example when you have this improper rotations. Okay. A little bit more about improper rotations. Suppose I do S4 times S4. Okay. So, what will I get if I do S4 times S4? So, to understand this, you can just say this is C4 sigma times C4 sigma, and we already said that C4 and sigma, since sigma is in a perpendicular plane, it commutes. So, I can write it as C4 square sigma square. Sigma square, sigma being a reflection, sigma square is the identity operation. So, this is just C4 square, C4 square, and C4 square is actually C2. So, C4 square is the same as C2. Okay. So, you can always take it to the lowest factor. So, rotating by 90 degrees twice is the same as rotating by 180 degrees once. Okay. So, C4 square is C2. Okay. So, now we can repeat this for all, we can generalize this to any Sn axis, and that is what I will show next. So, Sn equal to Cn times sigma, Sn square, okay, is Cn square, okay, because sigma square is identity. Sn cube is equal to, so I can just write it as Cn cube sigma, Sn4 equal to Cn4, and so on. Okay. Now, what is Sn raised to n? Sn raised to n is Cn raised to n times sigma raised to n. Okay. Now, Cn raised to n is nothing but identity. So, this is sigma raised to n. Okay. Now, sigma raised, I will write it right here, equal to sigma raised to n. Now, sigma raised to n, this is equal to identity if n is even, and equal to sigma if n is odd. Okay. So, Sn raised to n is identity only if n is even, otherwise it is equal to sigma. So, if Sn is odd, so S5 raised to 5 will give you sigma, S7 raised to 7 will give you sigma. Okay. So, but you can say without any problems, you can say that Sn raised to 2n. So, this is Sn raised to n square, that is sigma square, equal to identity. So, Sn raised to 2n is always identity, whether n is even or odd, this is equal to identity. Sn raised to n is identity if n is odd, and it is sigma if is identity if n is even, and sigma if n is odd. Okay. So, there is one last property of this improper rotations that I want to mention. Okay. So what is S2? Okay. So what is S2? Okay. And you can show yourself that this is C2 times sigma, which is just exactly equal to the inversion operation. Okay. So, if you rotate by 180 degrees and then you reflect about a perpendicular plane, you get exactly the same as the inversion operation. Okay. So, as operations, these two are the same, S2 equal to I. Okay. So, if you say a molecule has an S2 axis, it is as good as saying that the molecule has a center of inversion. Okay. So, next we will look at representations of these operations. Okay. Now let us talk about products of symmetry operations. So what happens when you operate by a product of symmetry operations? We will use a notation. The following is the notation we will use. Suppose I want to say, suppose I write C3 times sigma. Okay. Suppose I write C3 times sigma. What I imagine is that I have, this is operating on the molecule. So first sigma operates on the molecule and then C3 operates on the molecule. Okay. So this is sigma operation followed by C3 operation. Okay. So we will be using this convention for products of operations. Okay. So whenever I write C3 sigma, that means I first operate by sigma and then I operate by C3. Okay. So let us ask a few questions. What is the product of two rotation operations? Okay. So suppose I operate by Cn and then I operate by Cm. Okay. Now if both Cn and Cm are the same axis, if they point along the same axis, then obviously rotation once by m by 2 pi by m followed by 2 pi by n turns out to be another rotation. Okay. So if you are, this is, so it is if n and m of Cn and Cm are along same axis, then Cn times Cm equal to rotation by 2 pi by m plus 2 pi by n is equal to rotation by 2 pi by m plus 2 pi by n. Okay. And if you want, you can write this as 2 times 2 pi divided by m n by m plus n. Okay. So this is C m n by m plus n. Okay. So if they are along the same axis, then rotation by so if m is 3 and n is 2, okay, so that is 3 corresponds to 120 degrees, 2 corresponds to 90 degrees, okay, 2 corresponds to 180 degrees. So 120 plus 180 is 300 degrees. 300 is same as 2 pi into well, it is the same as 2 pi divided by 6 into 5. Okay. So m equal to 2, n equal to 3, then C2 times C3 is equal to rotation by 2 pi divided by 6 into 5. So 5 by 6 into 2 pi, that is 300 degrees, which makes sense because n is m is 2, so that is 180 degrees. So Cm corresponds to 180 degrees, n is 3, so Cn corresponds to 120 degrees. 180 plus 120 is just 300 degrees. Okay. Now if Cn and Cm are not the same axis, okay, so the statement is that even if Cm and Cn are not the same axis, Cm times Cn is a rotation. Okay. So you can prove this, that a product of two rotations is a rotation. It might be about a third axis, about some axis. Okay. So in other words, product of two rotations is another rotation. And I must emphasize that I have not proved this. Okay. But you can go ahead and you can actually show that this is the case. Okay. The proof is rather lengthy, but it's not too hard to show this. Okay. So next, so the product of two rotations is another rotation. What about the product of two rotations? So what is the product? Is the product of two reflections. Okay. Now if they are the same plane, then obviously the product of reflections is identity. Okay. If they are not the same plane, so in planes making angle theta, okay. So if you reflect about one plane and then you reflect about another plane that makes an angle theta, okay, what is the product of these reflections? Okay. And the answer is that the product of these is a rotation by theta, rotation by 2 theta, Okay. So the product of two reflections in planes that make an angle theta with each other corresponds to a rotation by 2 theta. Okay. And if you remember, when we were looking at the D6, the dihedral group of order 6, we had two reflections, okay, and the product of those reflections turned out to be a rotation. Okay. So in general, the product of two reflections, okay, corresponds to a rotation. Okay. So this is a general rule, and this is very helpful when you are making the character table. Okay. Then the other thing is, what are the various operations that commute with each other? Okay. So what are the various operations that commute with each other? So that will be the next question. So we said that a rotation and a reflection in a perpendicular plane, they commute with each other. So are there other sets of operations that commute? Okay. So operations that commute, in other words, x y equal to y x. Okay. So operations that commute, I will just make a list. So I commutes with all other operations. Next, C end about the same axis. So any rotations about the same axis, they commute with each other. Reflections in perpendicular planes. So if you take two reflections in perpendicular planes, they will commute with each other. So and then we also said that rotation followed by or rotation and perpendicular reflection. Okay, so that is reflection in a perpendicular plane, they commute with each other. Okay. A few other things I want to mention is that S, we saw that S2 equal to I. Similarly, S1, what is S1? S1 is just sigma. Okay. So, these two are identically equal to each other. So, you don't, so you never actually use S1 and S2. Okay. You never use S1 and S2 because S1 is, S2 is just I and S1 is just sigma. Okay. So, you don't use, so never use S2, S1. Okay. So, that is the other thing. Okay. Next, we will come to the concept of optical isomerism. In order to do this, we have to introduce the concept of mirror image. Okay. So we have to introduce the concept of mirror image. So, we are going to talk about optical isomerism. In order to do this, we will say what is a mirror image. Okay. Now, I will do this with an example. So it becomes very clear and there are no confusion. Suppose I consider the molecule of this form A, B, C, D. Okay. I can reflect it. Okay, so I can reflect it about a plane like this to get B, A, B, C. Also, if I want, I can reflect about a plane that is this way. Okay, so if I reflect it about this plane, then I will get something that looks like B, D, C, and A. I can reflect it about any other plane. I can take various other planes. I can take a plane that goes like this. I can take a plane that goes like this. I can reflect it and I will get various other configurations. Okay. Now, the question is, which is the mirror image? Image. Okay. So, the answer to this question is all are mirror image. All are the same mirror image. Okay. So, the same mirror image. So, this and this are the same mirror image. Okay. So, how is it that you said these two are the same? The reason is that if you just turn this around, you will get this. Okay. So, when discussing mirror images, we can turn molecules. Okay. Okay. So, whether I take this as a mirror image or this as a mirror image, I can always turn it. I can turn one around and I will get the other. Okay. So, in other words, there is only one mirror image for any molecule. Mirror image for a molecule. Okay. So, there is only one mirror image for a molecule, and so a molecule that is not superimposable on its mirror image. A molecule that is not superimposable on its mirror image is said to be disymmetric, is dissymmetric. Okay. So, a molecule that is not superimposable on its mirror image is dissymmetric. Okay. This is different from the term asymmetric. Asymmetric is a molecule that does not have any symmetry element. So, asymmetric means no symmetry element, no symmetry. Okay. And asymmetric obviously implies dissymmetric. because asymmetric implies dissymmetric, but dissymmetric, but you can have dissymmetric molecules that have symmetry elements, okay, which are still not superimposable on their mirror image. Okay. So, what is the condition for a molecule to be dissymmetric? So, for a molecule to be dissymmetric, it should not have any SN. So, it should not have any improper axis of rotation. Okay. So, a molecule that does not have any improper axis of rotation will be dissymmetric, okay, and dissymmetric molecules show optical activity. Okay. So, in other sense, they rotate the plane of polarized light in one direction. Okay. So, dissymmetric molecules show optical activity, and you have various optical isomers which you have studied in your organic chemistry courses. So, the condition for a molecule to be optically active is that it should be dissymmetric, or it should not have any SN axis.